Alright guys, welcome to part 2 of the Power Series lesson, and for this one we're going to go over the last objective here, which is being able to differentiate and integrate terms of a series to create a new one. Now I'm going to show you for this first example two different approaches, and in my opinion, depending on the problem, one situation might be better than another depending on your comfort level. So the first method I'm going to show you is what I would prefer, I think is the most efficient way, and that is using the notation here to actually take the derivative. So what we need to first look at when we actually look at this series here of x raised to 5n over n factorial is that the n factorial is a coefficient at the end of the day, whereas the x to the 5n, whoops, that should be a highlighter, not a line, that is going to be an actual function that I could take the derivative of. So if we were looking, for example, here to take the derivative of x to the 5n, what do we use? We will use our favorite series from the or our favorite rule, I should say, which is the power rule for derivatives. So what would you do in this situation? Well, think about what would you do if it was x to the 5th power or x to the 10th power. You would drop the exponent in front, so in this case it'd be 5 to the n, and then you would reduce the exponent by 1, so it'd be 5 to the n minus 1. So that's exactly what we're going to do here to write our new series. So this would be f prime of x is equal to the series here. Again, the only thing that's changing is that numerator, so this would become 5 to the n, x, 5 to the n minus 1, and then the n factorial remains, okay? So we're technically good there. And what we can do now is we can actually start writing out now the first three non-zero terms and our general term. Now, here's the weird thing with this problem. If we actually start with 0 here, we're going to get a 0 term because we would have 0 over 0, which brings me to a little sidebar here of what we can do to actually simplify this problem. Now, the good news is if you didn't recognize what I'm about to show you, you're still going to be fine because you would just write 0 plus, and then you would just that next term would actually be your first non-zero term, and then you would still get the exact same answer that we're going to get this way. Okay, so we're going to go on a little side quest here to talk about what to do here with this n over n factorial. So remember, we use this back with the ratio test too, that you can actually write n factorial as n times n minus 1 factorial, which then allows me to cancel the n's out. So my final simplified term here is going to be n equals 0 to infinity. So now it would be 5x to the 5n minus 1 over n minus 1 factorial. Now, there is one thing we have to make now as an official adjustment here, because if I were to actually plug 0 in right now, we would get negative 1 factorial, which is not going to work. So remember I talked about that non-zero situation? So we're actually going to start our index here at 1 so that we will actually be able to get a non-zero term to begin. And so that's actually what we're going to do. We're going to go ahead and find those first three non-zero terms. So we have our general term. Let's go ahead and let's write the first three non-zero terms. So if I plug in now 1, we would get 5, and then it would be 5 minus 1, so 5x to the 4th over, that would be 0 factorial, which is just 1. So we're just going to go ahead and write plus now and move on to the next term. And then the next term, we're going to plug in 2. So if I plug in 2 to this, once again, we'll have that 5. We're going to get 2 times 5, which is 10, minus 1 is 9, so x to the 9th over, now we would have 1 factorial. I'll write that, even though we know it's 1. All right, we have one more term, and then we're actually done. The next term would be 5, and then we're going to plug in 3. 3 is 15 minus 1, so it's x to the 14th, and then that would be all over 2 factorial. So that would just be, well, 2. So that's going to be our first three non-zero terms plus dot, dot, dot. And so this would be our final answer. General term is what we have in the series here, as well as the first three non-zero terms. Now, before I go on to the last example in this video, I do want to mention I said there was a second method. So I'm just going to show it to you here already finished. And this would be if you actually wanted to go through and do it manually. So what you could have done, rather than taking the notational derivative like I did here and then create the terms, is that we could have actually created the terms first from the original f of x definition. And then I simplified it a little bit here, and then just actually take the derivative. So this would become 0. That's why that non-zero situation we had mentioned, this would become 5x to the 4th, this becomes 5x to the 9th, and you'll see that matches the first two terms we have. And then this last term, now 15 over 16 simplifies to 5 halves, which is what we have here, at x to the 14th. And then notice that the general term here, if you didn't notice that trick earlier, you would have it as 5 to the n over n factorial here. That would have been acceptable as well, but this would be another approach, is to create the function and then manually take the derivative yourself. In fact, for our final example in this video, we are actually going to do it using that method. So in this last one, we're going to be asked to find the first four non-zero terms of the Maclaurin series represented by the integral. So this is going to kind of merge the last two examples that I showed here together. So the first thing we're going to do is we're going to go ahead. Now I'm going to skip ahead. Instead of just writing out the sign terms, I'm just going to go ahead and create that skeleton here. Normally this will be x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. But I'm going to go ahead and just save us a step of writing here, and we're going to go ahead and plug in t to the 7th in for x like we did back in example 2. Okay, so there we have it. I'm still going to write the plus dot dot dot. Thankfully, they're not asking for a general term here, so we don't have to worry about any of that notation. Okay, so it looks like we found that here. Now, the last major thing we have to do is we have to actually integrate this. So we're going to integrate this from 0 to x, and once again, that is our sine of t to the 7th dt. So we'll go ahead and write that in just like that. And so what I'm going to do first is I'm going to go ahead and take the antiderivative of each. So this is going to be t to the 8 over 8. Now these are 21, that's 35, and that's 49. So just keep that in mind as I'm writing these answers here. This will be minus t to the 22nd over 22, but we have that also that 3 factorial in there. This next one's going to be t to the 36 over 36 times 5 factorial. Don't even worry about simplifying these. 9 times out of 10, a problem like this one I'm going over would be a multiple choice question anyways, so you're just looking for a pattern. This would be then t to the 50th over 50 times 7 factorial, and then we have our dot dot dot. But we're not done yet because we still have to technically do the fundamental theorem of calculus, which tells me now that I found the antiderivative, we have to evaluate it at the upper limit x, the lower limit of 0. Now here's the good news. The lower limit of 0, notice that these all are going to be 0 over something, so we don't even have to worry about that. And then the upper limit is just x, so we would quite literally just write this as x squared over 8 minus x to the 22nd over 22 times 3 factorial, and then we would just simply finish writing all of these out. So there we are. So these examples, I know there's a lot here and there's a lot in this entire unit, but this is going to be the ultimate culmination. And what I will tell you is that problems involving power series, ones that I've shown in this video, as well as the last couple lessons of power series, like finding the radius and the interval of convergence, all of these things are very common free response questions. So the advantage here is we have a plethora of FRQ questions from prior years that we can go back and look at to really see the expectation of what you would be expected to see on the AP exam. So that's my recommendation, and you'll notice that a lot of the practice that you're going to do, there's going to be some multiple choice practice that you're going to do, but then after that, you're going to jump right in and do a bunch of free response questions. And we're going to go back from the last prior years and really try to look at those problems and see if we can identify some general patterns and notations that you will do in most of these FRQs. So I ask you to do your best as always, and congratulations. At this point, we are finished Unit 10. Congratulations on that. Have an awesome day.